So you have to send me the link, YouTube link. Can I start? Okay. Is there a way to hide this video on the YouTube link and just see only the chat? Okay. Because this is a big distraction. This video appearing with the time lag is a big distraction. Good evening all. For those who have joined, welcome to the week 2 interaction session. I would, before you start asking your questions, I'll just quickly review what we did in week 2, what you are supposed to learn during week 2. So week 1 was more about the fundamentals of digital communication, some basic definitions of the bit rate, different types of modulation, constellation, and so on. And in this week, we initially saw a very important theorem, which is the Shannon's theorem, and that basically decides the capacity that can be transported in a linear channel. Then we moved on to the block diagram of an optical communication system, and we also saw, we started with the blocks, and the first block in any communication system is the source, right? And so we started, last week was about, or rather this week was all about understanding how understanding how a semiconductor light source works. So we first took up the case of LEDs, and before we started LEDs, I gave you a small primer on the different possible ways of light matter interaction. Then we talked about absorption, spontaneous emission, and stimulated emission. Then we talked about the specific heterostructure design, which will help carrier confinement and also the light confinement in an LED structure. So that was one of the landmark inventions, I must say, that enabled the carriers to be confined and the light to be confined, and that actually improved the efficiency of the process and made this practically feasible. Then we also talked about band gap engineering, where we try to mix compounds from the third group and the fifth group and try to mix the dopants in such a way that now you can get a desired band gap. Later on, we moved on to trying to understand what is the probability of emission. So we decided, we discussed a bit about the two factors that influence the light emission spectrum. The first factor being the density of states. So if you, in a semiconductor, you know that there's a continuum of energy states that are allowed. So the first factor that influences is whether the energy states are available. And the second factor that influences emission is the occupation probability density, joint probability density, which means that you need to have states, and then you need to have these states occupied by electrons in the conduction band and holes in the valence band, so that they can recombine, and hence you can have emission. We did not really derive the density of states and occupation probability, but we intuitively give you a very heuristic picture of how these two factors influence the emission spectrum. And once you write down the expression for the emission spectrum, it is very surprising to know that doesn't matter what your LED is made of, the bandwidth is 11 terahertz, which is really a very intriguing thing, because you can make LEDs of different colors, different compositions, but turns out the bandwidth is 11 terahertz. Then we moved on to deriving what is exactly the power emitted by LED. Essentially, the number of photons, we started converting that into energy and power. And there we realized that even though the LED can emit a lot of photons, what you can extract it out of the LED structure is limited, primarily because of Fresnel reflection, absorption, and total internal reflection. So there we defined the external quantum efficiency, and then we talked about wall plug efficiency. And unfortunately, the net efficiency of an LED was very, very limited, and the primary limitation was coming because of total internal reflection. Of course, these days there is research going on and improving the extraction efficiency of LED. Can I make some structures outside the LED so that my extraction efficiency is larger? So those things we can discuss. After that, we touched upon a very important aspect, which is the modulation bandwidth. So remember, there are two bandwidths we are talking about. One is or rather, in terms of spectrum, we are talking about two kinds of spectrum. One is the emission spectrum. So what are the carrier wavelengths that I can get out of the system? And the second is the modulation bandwidth, where you're saying that, look, I choose a particular carrier, and how fast can I now modulate around that carrier? So that is your modulation bandwidth, and we derived the expression for modulation bandwidth. I told you the difference, the subtle difference between optical bandwidth and electrical bandwidth. This is very critical when we are trying to design a transmitter. And at the end, we talked about the emission pattern of LED and how we can calculate how efficiently can we couple the light from an LED to a fiber. After that, we moved on to laser diodes, and then the first thing we did was to point out what are the limitations of the LED, so that we are actually forced to learn about laser diodes. And turns out that the fundamental limitation is modulation bandwidth, the large spectrum, and essentially the speed of response, the large spectrum, and the efficiency. That's where we realized that if you were to change fundamentally the speed of response, you need to make these carriers respond faster. You need to make these transitions happen faster. So you need to do a different process. And so you looked at stimulated emission. And turns out that the stimulated emission rate is much faster than the spontaneous emission rate. And hence, the laser gets all its benefit because of its stimulated emission. And the primary requirement for a stimulated emission is feedback. And so we started spending time about what is a feedback system in an optical scenario. In electronics, you have learned feedback. In an op-amp, you would have learned how to do a positive feedback and so on. But in an optical system, how do you do a positive feedback? That is by using a resonator. So we derived the basic, the gain and amplitude and phase conditions for a Fabry-Perot resonator, which is probably the most commonly used resonator to build a semiconductor laser. And we derived what are called as, we defined what are called as longitudinal modes, and also the conditions for the frequencies, allowed frequencies in the system, which is dictated by the length of the cavity, the refractive index, and so on. And we also tried to see what is the spectral width of one single longitudinal mode. That's where we stopped. Okay, so this was last time's work, this current week's work. Now, there are a couple of questions which I would like to address before I start addressing your chat questions. One question came up during in the course discussion forum. Was that I said in the when we were doing light matter interaction, I said that doesn't matter whether it's an LED or a laser, you need population inversion. And somebody had asked a question that, why would you need population inversion for an LED? We have learned that population inversion is a requirement only for laser diode. Now, the point to make is, you have learned whenever you have photons interacting with the material, there's either absorption or emission. Okay, so if let's see if I can pull that diagram. I'm trying to share my screen here. I hope my screen is visible to you. Uh, I hope you're able to see my screen. What I wanted to show you is that yeah, this is what I wanted to show you. So you need to have, whether it is a LED or a laser, you need to have some carriers in the conduction band. You need to have excess carriers in the conduction band so as to have emission. Suppose you do not have excess carriers in the conduction band, what will happen is all your, if you have an incident light or if you do not have this carriers in the conduction band, the probability of absorption is more than the probability of emission. So in net effect, what you will end up having is more absorption rather than emission. And hence, when I say population inversion, it means that you need to have electrons available in the conduction band so that they can recombine with the hole and create emission. So that is why we say that even when in the case of LEDs, of course, in stimulated emission, you need to have these photons interacting with the electrons in the conduction band and stimulate the whole process. But even for spontaneous emission, you would need a population here, otherwise there is no emission. That's what I meant. So that's one question that needs to be clarified. And the other thing I need, to clarification is that somebody had also asked, a given carrier either undergoes radiative transition or it undergoes non-radiative transition. So why should I when I write the rate equation, why should I take both? So we are writing the probability of radiative or non-radiative transition. So in terms of writing the probability, this you do not know whether this given electron in the excited state is going to undergo radiative transition or non-radiative transition. So in the rate equation, what you're doing is you're trying to write down the probability of transition. So you have to account for both radiative and non-radiative transition. You're not writing the rate equation for one electron in the conduction band, or you are writing it for n, right? So if n is the number of is the carrier density, you're trying to write the rate equation for that carrier density. You do not know a priori that a specific carrier is going to undergo radiative or a non-radiative transition, which is why you have to consider both. Now I will take up questions from the chat window. What is the difference between, so let me first again repeat, please ask questions that are relevant to week 2 so that it's useful for everyone. So those questions which are not relevant to week 2 content, I'm just going to ignore. Basic difference between step index, I'm going to ignore. Molar concentration and at band gap engineering. So band gap engineering is actually a slightly complicated topic of discussion. We will not, that's actually a topic for semiconductor devices course. All what I can say is that by controlling the proportion of you take, for example, we took the example of indium gallium arsenide phosphide. Let's see if I have again a diagram to show you that. Give me a minute. So let me present my, share the screen. You see, for example, indium gallium arsenide phosphide. This is a compound semiconductor. This is a compound made of 4 elements. You have indium, you have gallium, you have arsenic, and you have phosphorus. Now, in this compound semiconductor, it turns out, and this formula that you see on my screen is actually something that came up as an empirical formula. I'm not sure whether anybody can derive these formulas. I mean, there's no analytical derivation. So it turns out that if you are trying to take, for example, gallium arsenide, and then you dope it with indium, you dope it with phosphorus, and you dope it with this proportion, which means that if you can think about it as if you have X proportion of gallium and 1 minus X proportion of indium, these are, you know, different semiconductors of different groups, and you're trying to make a compound semiconductor. And depending on the proportion with which you are adding or making these semiconductors, you can engineer the band gap. You can decide, you can find out what the band gap. Unfortunately, we won't be able to take up more details about this because it's completely semiconductor device topic. So we just take the result from them and saying that you can end up. So this is only one example of indium gallium arsenide phosphide. You could take different compound semiconductors and you can use different proportions. That's all available in the materials, book of materials, or, you know, encyclopedia of materials kind of thing, and you can mix them in different proportions to engineer the band gap. What's the benefit of engineering the band gap? Because now you know that the energy that comes out of the semiconductor, the minimum energy that comes out of the semiconductor, is decided by this band gap. So I hope that answers that question. We will move on to the next question. In an optical fiber communication system, can we use LED instead of laser? So, Senthil, I don't think you have watched the first lecture on lasers, where we are, I'm trying to say what is the limitation of LED. So, we very clearly say that if there is a large bandwidth, LED has a large bandwidth, and you transmit with large bandwidth, what happens is the fiber is carrying a huge spectrum, and that undergoes dispersion. And what is dispersion, we will learn later. So it simply means that the different frequency components are traveling with different speeds, and so your information is going to get spread out in time, because the certain wavelengths will travel faster, so certain wavelengths will travel only slower. So by the time you reach the receiver, the information is going to get spread out in time. That is dispersion. And because of that, you do not prefer to use LEDs for any long distance kind of communication. Having said that, you could use them for short distances at 1300 where the dispersion is low, and so on. We also said that the modulation bandwidth of LED is limited because of the carrier lifetime, right? So if you were to design something very fast modulation, again, LED cannot be used. The next question is from Monojit. In which way laser diode is beneficial for optical communication? So this is coming back to the same question. Please go back and read that lecture again. The first lecture on laser diodes, I've told you what are the differences. I'm going to ignore these general questions on what is the future trend of OFC and so on, because this has been discussed last time. See, again, I explained to you, I mean, you can ask me general questions, but, you know, please try to ask these general questions in the course forum. Use these weekly sessions just to discuss the contents of the week, so that we can all stay focused in understanding the contents that were discussed during the week. The next question from Satvik is, in heterojunction, how in heterojunction, low band gap, so we get high refractive index, but in spectral width, it's totally opposite. I am trying to understand what this is. Satvik, can you please rephrase your question once again? Because I didn't quite understand your question. Can you please try asking this once again in a slightly different wording? Or if somebody else is able to make out this question, can you please rephrase it for me? I'll wait for that. In the meantime, let's take the question from Vishwanath. Whether absorbed power is equal to, oh, this is another thing I wanted to point out. Absorbed power is equal to initial power into exponential minus absorption coefficient into propagation length, or it is equal to initial power into. So this you should have guessed. This was a goof up there. You see, I have a certain power P falling on my system. Let me see if I can write it down. Okay. Let's see. I hope you have able to see my screen. I have to keep my tablet in a different direction. Let's say P naught is a power incident in a medium, and let's say the medium has an absorption coefficient of alpha, okay, and this is the Z is the extent of the medium. What comes out of the medium is P naught exponential minus alpha Z, which means what got absorbed in the medium is P naught minus P naught e power minus alpha Z. So this is P naught times 1 minus e power minus alpha Z. This is the power absorbed. If you found it different in any place, my apologies for that error. This is what it is. If I have P naught falling on this medium, again, alpha is this absorption coefficient. And you know that if you write it as an absorption coefficient, it's an exponent. This is in the units Nepper per meter. So that this meter and this Z in meter can cancel, and you get a dimensionless, or you get it in Neppers. And when you do an exponential with Neppers, this becomes this part. Sorry, this part becomes a dimensionless quantity, and this tells you the fraction that comes out. So obviously, what is absorbed would mean P naught into e power minus alpha Z. If there was a mistake there, I apologize, and we will go back and correct that. Explain the spectral width of LED and how to calculate this. So Vasundhara, I will direct you to the specific video. Let me try to see if I can get that. So let me just say this way. I just want to make sure whether you're able to see what I'm writing on the screen. Okay, so now that you're able to see this, so there are the spectrum. One is, as I've explained in my lecture, I'm just explaining it once again. The minimum energy that comes out of the system is decided by your band gap. And that is given by Eg is equal to h nu. Because this is the lowest state from which the electron can undergo transition and reach to this point, right? So this is the minimum energy. So this is h nu minimum. So if I'm trying to draw the spectrum that is emitted by a laser, this minimum, nu minimum, is given by Eg divided by h, which is why you wanted to do the band gap engineering. Now, what is the largest frequency that can come out of it? That is decided by largest energy. So the largest energy, let's say this is some arbitrary energy state I'm drawing, and here is where my the emission energy, I can represent the energy coming out here as h nu. I don't know whether it's the maximum, but the question we're asking ourselves is how high in the energy level diagram can I go? So in the lecture, I've explained that this is decided by two factors. One is density of states, which means whether you have energy states available here, right? That's your density of states. And the second is occupation probability, which means what is the probability of occupation of this by an electron and this state, or I'm sorry, this is not coming out very neat, but what is the probability that you have an electron occupied in this state and a hole occupied in this state, so that there is a transition. So there is a joint probability of occupation. The product of these two probabilities actually gives me the probability of emission, and the spectral dependence of that probability of emission is my emission spectrum. So I kind of told you that, in fact, I did not derive, I said that one of these, the density of states is proportional to square root of h nu minus Eg, and the occupation probability is proportional to e power minus Eg by kT. So the spectrum is decided by this quantity. This root of h nu minus Eg evidently tells you that you cannot have your nu which is smaller than smaller than Eg. That gives you the nu minimum here. Now, if you look at this quantity here, you will see that that's an exponentially decaying quantity. So, sorry, this is also h nu minus Eg by kT. So, as a result, you will get a function something like this if you plot that function. This is also h nu minus Eg by kT. Okay, so this is not Eg, this is h nu minus Eg by kT. Right? So what? So the question is now, how do you get the maximum now? How do you get the maximum of this function? Now that's a very algebraic mathematical process. If I have a function which is of nu, a function of nu, I want to find where the maximum is. I will do the derivative of this function with respect to nu, which means I'm going to do a derivative of this with respect to nu and demand that it is equal to 0 at the maximum. And this, so you have to do a derivative of this product of these two functions as a function of nu and demand it is 0. And then the nu that will satisfy this will give you nu max. Now you can also find the full width at half maximum by saying that, look at this point. So let me try and draw this spectrum once again. So you have, this is your spectrum. This is your nu max. And you want to find out two frequencies for which this spectrum value, let's say the maximum you normalize to 1, this becomes half. So you say this is nu1 and this is nu2. And now you can demand that the value of this function should become half at nu1 and nu2. And then you find out what is that nu1 and nu2 for which the value became half corresponding to nu max. How do you know the value corresponding to nu max? You already know nu max. So you substitute here, substitute nu max in this expression. you will know the value corresponding to this, which is actually, I just wrote it as 1, but it is not 1. This value is actually that constant, whatever constant we took, into h nu minus Eg, square root of h nu max minus Eg, square root of this, into e power minus Eg by kt, h nu minus Eg by kt. So, well, this term in the exponent is h nu max minus Eg by kt. That is what you will have minus of this. That's what you will have at the peak. Now you find out what are those frequencies for which this value comes to 1/2 of the peak value. That will give you a nu1 and nu2. The difference between nu2 and nu1 will give you your full width at half maximum. So that is how you calculate the FWHN. It's a question from Michael. Why Maxwell-Boltzmann is not followed in LED? So you see, it's all transitions of electrons that we are talking about. So it would mean that you need to you're actually talking about the statistics that the electrons follow, and that is Fermi-Dirac statistics. That's not Maxwell-Boltzmann statistics. Pulse dispersion in fiber optics we're going to do in detail, so we will take it up at that point. Mukesh Kumar is asking, why do you need modulation? You need modulation. Without modulation, you cannot transfer information. Your carrier has to get modulated with your data so that you can transport the information. So why is modulation necessary is already done in week 1. Please go back to those lectures. So another question from Michael, which is, in rare earth ion gain medium, we have level 2, 3, 4, but in LED, it's 2-level conduction or valence. Does it mean that LED or laser diode is less efficient? So this is a very interesting question. You do have, so the question that Michael is asking is the following. So again, let me try to share a place where I can scribble. I promise that by next week, my scribbles, I'll try to get my scribbles in a better fashion. Right now, I'm using a blind tablet where I'm not very comfortable with. Okay. So the question asked is, in case of rare earth emission, which is like erbium or ytterbium or any such rare earth optical emission, you would have learned there is a lower energy state, then there is a higher energy state, and then there could be a metastable state in between, and so on. These are discrete states or even closely closed states near the allowed states. Now, this is happening in a dielectric, right? Whereas in a semiconductor, we know that you cannot have distinct energy levels. What we will have is a continuum of energy levels, and then you talk about density of states. Now, in general, the process of stimulated emission, etc., is the same. You have to just imagine that these states are instead of these from these specific levels, now you can have emission from a continuum of levels. But as far as the efficiency goes, the question was, would this be less efficient than this? As far as the efficiency goes, so what decides the efficiency of actually emission? It is decided by the number of ions. So let's say if you take the stimulated spontaneous emission rate, it is n divided by tau, where tau is the lifetime in the excited state. So as far as efficiency goes, it is just decided by the carrier concentration here and tau here. Now, if you try to compare the same thing with here, you will have to now look at what is the dopant concentration, what is the excess dopant concentration in a higher state. For example, in this state, what is the excess, if this is N1 and this is N2, here you will look at N2 minus N1, and then you will look at divided by tau spontaneous, and that will give you the rate of spontaneous emission in these two. In general, the dopant concentration that you can have in dielectric, if I understand correctly, is more than the dopant concentration that you can have in a semiconductor. So it turns out that you will always get larger light from a dielectric source than a semiconductor source. Right? For example, you can make lasers from these dielectric sources, which are of the order of kilowatt or even watt or kilowatt. But as far as semiconductor system goes, to create this inversion, you need to send to create this inversion. So this is, let's say, a semiconductor laser or semiconductor LED. You will have to send a current. Now, the inversion that you can create is decided by the current that you are the injected carriers, and this injected carriers gets limited by the breakdown voltage, or rather the largest current that you can send through a semiconductor structure. And because it is a semiconductor structure, you have the depletion region, which is very thin, where all the action happens. You cannot flood this region with very large current, and because you cannot obviously send amperes of current unless your diode is specially designed and so on. So essentially what I'm trying to say is that the current that you can inject, and hence the inversion that you can create in a semiconductor structure, is actually much smaller. Whereas here, what you will do is you won't do electrical pumping, you will do optical pumping. This N2 carrier inversion is carried out by sending another laser. So this is optical pump. So in general, optically pumped systems are more efficient than electrically pumped systems, just for this reason. So I hope that clarifies. Let's see what's the next question. The next question is from Rajat. We know that larger band gap means lower refractive index. Okay, so this is rephrasing. Thank you, Rajat. Larger band gap means lower refractive index for better optical confinement. Oh, this is a slightly different question. Is there a specific thumb rule to maintain it? Maintain it or probably generate it. So the only thumb rule is that, let me go back to my screen again. You see, when you walk, the cross section of the semiconductor heterostructure is going to look like this. Here is a smaller refractive index. Here is larger refractive index. Here again is smaller refractive index. Right? Correspondingly, the band gap would have been the other way around. But I think the question what Rajat is asking is, how do I now decide what should be my band gap difference, or what is the thumb rule, or how do I now maintain this? What decides this band gap difference? So that's actually a very interesting question. It depends on what is the refractive index profile I desire from the system, right? So it depends on this dimension is fixed. This is the width of the depletion region. Now the next thing you are able to control is this N2 minus N1, which is N is the refractive index, and you are able to control the refractive index contrast, delta N. Now what happens for different refractive index contrast is that you will learn later, but I'll give you a primer. we learned about longitudinal mode, which is the mode along the length of the propagation of light. But from an LED structure or from a laser structure, there's something called as a transverse mode, which you would have come across if you have learned waveguides. Whenever there is a boundary, when you say boundary, it means a different refractive index or different epsilon in general. When light encounters, it's propagating through this boundary. So all along the length of the waveguide, you have this boundary. It means that the light gets confined here. Now you can talk about modes which have different transverse profiles. So I'm just drawing the fundamental mode of any two-dimensional dielectric boundary, which looks like a Gaussian. We will talk about this boundary again when we talk about optical fibers, where we discuss more about transverse mode. But all I want to say now is, depending on the choice of your EG, you are deciding your N2 minus N1. And this N2 minus N1 actually decides what is the nature of the transverse mode that is supported by the LED or laser structure. So if you want it to be a single transverse mode also, you have to pay attention to what your N2 minus N1 difference is, and this, whether it is one transverse mode or whether it is multiple transverse mode. Multiple transverse mode again is also not ideal for light to propagate through the fiber, because again, multiple transverse mode means that you would have, let's say the fundamental mode is this, the higher order mode is going to look like this, right, in terms of electric field. So you will have a null in between and you have a maxima on either side and so on. So you would want your source to be a single transverse mode system, in which case you would want to control your N2 minus N1, because this dimension is more or less kind of fixed for, or there are other constraints. Let me put it this way. There are other constraints which decides the width of this PI, the intrinsic region in between, or the depletion region in between. Whereas N2 minus N1 is completely controlled by band gap engineering. So you basically make sure that the refractive index profile is such that you can support only a single transverse mode. So that's how you decide your EG. There's a question from Shivalingappa. What is the difference between Raman and EDFA? That will come later in the course. So please be patient. Stay with the course. Increase in the refractive index or decrease will decrease or increase wavelength in case of Fresnel reflection. So I would say you ask this question. What is Fresnel reflection? Fresnel reflection is a phenomena that happens because of change in refractive index. So let me see if I can find this corner here. So in normal incidence, let's say this is you have an interface, and let's say this is a piece of glass of refractive index n. You have refractive index 1 here. The Fresnel reflection coefficient gamma for field reflection coefficient, which means reflected field by incident field, is n minus 1 divided by n plus 1. And so mod square of this is the power reflection coefficient, that is this. Now you can tell what happens when you increase n. You can basically plot this and check what happens when you increase n. You will realize that the reflection coefficient will start increasing. It's a question by Vishwanath. Whether Nyquist sampling rate and Nyquist shaping is related or not. Actually, these are slightly different concepts. We will Nyquist sampling is the from Nyquist theorem, the number of samples required to effectively sample a given bandwidth. Whereas Nyquist shaping is actually to do the time domain shaping such that you are able to transport the given information you are able to transport the information in the lowest possible bandwidth. Again, probably lecture 8 had that. Let's see. Maybe lecture 7. So let me just pull out lecture 7. Lecture 7 was Shannon's theorem. Lecture 6. Here. Okay. Let me share this once again. I hope you can see my screen now. So you see here, if you have a total bandwidth, if your bit rate is, let's say, B, let's take an example, 10 gigabaud is your symbol rate. In one symbol, you could have 4 bits in case of QPSK, or 16 bit, 2 bits in case of QPSK, or 4 bits in case of 16 QAM. But if your symbol is going at 10 gigabaud rate, and if it is a non-return to zero symbol, non-return to zero kind of pulse shaping, your spectrum is going to look like this. This is your carrier frequency. And here is where you have FC minus B to FC. Sorry, this is supposed to be like this. This FC plus B. Okay. This is if you do not do any kind of spectral shaping. Now, in the time domain, this is going to look like it's a non-return to zero pulse. So you have 1, 0, 1, 0, and so on. This is 1, 0, 1, 0. If it is a 0 and then again a 0, it doesn't, it just goes on like this. Now, this is what happens in a non-return to zero. Now, Nyquist's theorem tells that the sampling rate to transport a given bandwidth, it should be at least twice the bandwidth. That is your Nyquist theorem. But here, what we are talking about Nyquist shaping is that, for example, if this is power spectral density, so let's say this is power and x-axis is frequency, and here it is time along the x-axis. You could shape, you could, for example, instead of transporting it this way, you could actually shape your pulse in the time domain like this, and you could get a sharper spectrum. You could reduce the spectrum occupied in the frequency domain by doing Nyquist sampling, Nyquist shaping, Nyquist pulse shaping in the time domain. So essentially your S of t, which is your representation in the time domain, you pass it through a shaping function. We will talk about it later a little bit. When you pass it through the shaping function, in the time domain, it will look different, but in the spectral domain, it's going to look like very, very constricted. The question is, how much can you reduce this occupied bandwidth to? Here it was occupying 2B, but what is the smallest that I can, what is the smallest bandwidth that, I'm sorry, this is a complete mess. So let me just, yeah. So the question you're asking is, what is the smallest bandwidth you can reduce it to? And that is your Nyquist bandwidth. And this to this is your, or rather this B is your Nyquist bandwidth. Okay, so I hope that clarifies. So question from Arjun. The rate of non-radiative recombination depended on the quality of fabrication. Is it like if we reduce a number of defect states, we can get a better internal quantum efficiency? That is correct, Arjun. You see, the rate of non-radiative transitions. See, first of all, why do you have non-radiative transitions, non-radiative recombination? Because these electrons, instead of coming directly and combining with a hole, they are getting trapped in defect states. So if your semiconductor processing is not pure in that sense, or if there is contamination, what will happen is there are a lot of defect states. So these ions, these electrons will move from the conduction band to the valence band, but not through the radiative route, but through losing energy in different ways. And so that is correct, that if you reduce the number of defect states, your internal quantum efficiency can be better. How do you calculate spectral width? So Ayan is asking this question. So you have to explain to me spectral width in what context. We talked about different spectral widths. We talked about the emission spectrum of LED. We talked about converting from delta nu to delta lambda. We talked about, just now we talked about modulation baud rate in the time domain to frequency domain. So please again ask back what your specific question is. In which context are you asking about spectral width? Satvik has a question. What is the relation between band gap and refractive index in general in heterojunction? So I told you that band gap is inversely proportional to the refractive index. Again, these are empirical relations, right? So I really do not remember what exactly is the relation, but these are relations that you can find in the handbook of materials. And I've already shown you some of those relations, and it will come in the tutorial or the assignment also. Nobody has to remember this. This is all available. 50 years of semiconductor industry has generated enough data that we can just look at that and kind of use that as a empirical relation between band gap and refractive index. Devdatta is asking a question: gain versus frequency peak shifted due to temperature for lasers. Why is this happening? So Devdatta, you can answer this question now. It is not in lasers, even in LEDs, it is true. In any semiconductor, you will see that. Okay, let's see if I can draw it somewhere here. Oh, there's no space here. So let me open another page to scribble. Yeah. So what you're saying is that let's change the color. Gain or spontaneous emission, this saying is it shifts to the, as you change the temperature, it shifts to the right. Why? So you have, I told you that this relation is decided by two factors. One is density of states, which is not a temperature dependent quantity, but in the first approximation. And you have e power minus h nu minus Eg divided by kT, which is your occupation probability. The probability that you have the probability that you have a electron in the valence band and the hole in the conduction band, so that you can have a transition like this. So as temperature increases, what happens is the electron starts getting more and more energy, so they start shifting up. and that's the reason why you're seeing this effect. So it's primarily because of this quantity. Hope that answers the question. So Vasundhara is asking question, E is equal to H into F formulae. For all the numericals in assignment, can we take the product of H into frequency as 1.98 into 10 power minus 25 joule meter? Well, H into frequency will keep changing as a function of frequency, right? So you should just use Planck's constant, which is 6.635 into 10 power minus 34 joule seconds, and you substitute the frequency separately, meaning you have E equal to H nu. So as nu changes, your E will keep changing. The only constant here is H, which is Planck's constant, 634 into 10 power minus 34 joule second. So you can't substitute for nu something else. What you can also think of doing is, if lambda is what is given, you can do this as Hc by lambda, and you can find out this product and use that product because C is a constant. Somebody is asking हिंदी में बात करो. हिंदी में बात कर सकती हूँ, लेकिन मेरा हिंदी बहुत खराब है. I don't mind if you want a specific question to be answered in Hindi. I can attempt, but you should not laugh at me. That guarantee I can try to, because many words, you know, I live in Chennai. There is not much scope for speaking in Hindi in this place. So even though I know Hindi, my conversation is, I have not a lot of practice, but कोशिश जरूर कर सकती हूँ. तो कुछ सवाल आपको हिंदी में जवाब चाहिए तो बोल दीजिए. Where exactly do we incorporate the dome in the LED structure? Is it done before the boundary so as to reduce TIR? I'm a little confused. So Arjun, the dome is nothing to do with fabrication, right? So when they do the LED fabrication, you know, in the semiconductor LED fabrication, so you have the so let's say you have an emission happening from here. You know, this is the semiconductor material. The emission happens like this, right? The dome is external. In fact, people who make the LED, make the semiconductor, they are not the same people who may be fixing the dome, right? So the chip is made, it is cut into small pieces, and then you fix the dome based on, you know, it is external. It has nothing to do with the internal. So I probably showed you a picture like this in the class where you have this junction, right? And you have light emitting in different directions here. It comes back into, it gets back because of total internal reflection. What comes out is like this, right? Here is where you place the dome. I don't know if this is clear to you. Let me try to draw this once again. Here is where you place the dome, so that whatever light comes out of the structure, you are able to kind of focus it because this is kind of a lensing structure now, and you will be able to direct it in one direction. So hope that answers your question. Rajat has a question. Can you please explain the wall plug efficiency of LED? I still have a bit confusion. Let's see if I have the lecture notes on that. By the way, there was some lecture notes for week 1 is ready. Week 2, there was a small hiccup because of some peculiar reason. We will get it done very soon. Apologies for the delay. Let me just try if I can find the. Yeah, so I found this. So let me just try to show that. Are you able to see the screen? I hope you can see the screen. So we calculated three efficiencies, eta 1, eta 2, eta 3. And we also said the output is the output power is actually h nu by q times eta internal, external, and current. So this is like, now you can think of LED as a transducer, because you are giving an input electrical current and you are getting an output which is optical power. So and this is a linear relation, and we are very well know what is the relevance of this straight line passing through origin and so on. But when you talk about wall plug efficiency, this is again purely engineering concept, which says that what is the optical output power and what is the electrical input power, because you think about it as you're trying to calculate how much is the power conversion loss, right? I take a certain power from my electricity supply, whoever is supplying electricity. So there is a certain electrical power that I'm using, and this LED block is LED block is converting it into power optical. And what is the loss in the process, or what is the efficiency of the process? How do I quantify the efficiency with which I'm able to convert my optical power to electrical power to optical power? That is wall plug efficiency. So that is optical power output divided by electrical power input. So whatever P optical you got, which is here, h nu by q, eta internal, eta external, I, divided by current into voltage, because that's your electrical power. So that is wall plug efficiency. This P optical here, this P optical here is nothing but this P optical, right? So that's your wall plug efficiency. I hope that answers your question. If you are still not satisfied, please type in the chat window. Vasundhara saying, oh yeah, HC by lambda, you took it as 1.98 into 10 power minus 25. I don't know, 6.634 multiplied by 3 into 10 power 8. Is that giving you this number? It should match. If it is not matching, there's something else that is wrong. So we should check. Please send an email in the course forum, so that we can check which particular question you're having a problem. Vasundhara, please send it in the course forum. I'll take a look. Arjun, so yes, so the dome does not improve the external quantum efficiency. It effectively redirects whatever fraction of transmitted light. That is absolutely right. So the dome is not really to improve the quantum efficiency in that sense. Well, in one sense, you can improve quantum efficiency if you smartly place the dome in such a way that, for instance, if this is the material, it comes out, but then you don't allow this. So if this is plastic, so this is refractive index n, and this is refractive index 1, and so you had calculated the Fresnel coefficients that way. But then instead of this 1, suppose you're able to make it as a refractive index which is very close to N2, which is close to N, then the Fresnel reflection can be reduced. So essentially what I'm saying is you have this emission happening, and then if you're putting up plastic or whatever is the material, if this material has a refractive index N2 which is close to N, then it means that you can actually reduce the Fresnel reflection. So that way it can improve the external quantum efficiency. I don't see any more questions, so I will request people to type in your questions. I'm here around for some more time. So next week is going to be more about laser diodes, rate equations for laser diodes, and so on. So as you're watching these lectures, if you have questions, please keep asking in the course forum. Don't have to wait until today. Next Friday. And if there are let me see if there was any question in the Google Drive. Just a minute. Something that is not answered on the Google Drive. Okay, so there's a question in Google Drive which says, first one is about simulation software for free space optical communication. I've answered this again. I am not familiar with, I cannot recommend any simulation software because I have not used anything myself. It's better to always write your own codes so that you understand exactly what you're simulating. Modulation necessary, we have asked. In stimulated emission, when the photon strikes the electron in the conduction band, why the electrons won't move to the higher energy level? Why does the electron move from the conduction band and to the valence? Very interesting question. If there was a vacancy available in the higher energy state, essentially an electron hole recombination that was possible, then the electron would have moved. But then there's no vacancy in the higher energy state, because the density of states goes smaller as you increase the energy, and the occupation probability also goes smaller. So the probability of the electron moving down is more than the electron going up. Then there is daily life use of fiber optics. I'm not going to answer. Yeah, so those are the questions in the. Oh, there's one more question. What happens when different colors pass through the fiber? So Vignesh, we will talk about this a little bit more in detail when we talk about the dispersion in fibers. So I would suggest that just for now, you just understand that it's a bad idea to have too many colors or too many wavelengths passing through the fiber, which is carrying the same information. Because this information is, it's like dispersion, right? It's like, what happens in a prism. You send white light through the prism, they all split into different colors because, the refractive index for each color is different. The speed for each color is different. Same thing happens in a fiber. The speed for each color becomes different. So some colors appear faster, they arrive faster, and some colors arrive slower. So the same information now arrives over a spread duration of time, and that's not a good idea. We'll talk more about it. It's not just this chromatic dispersion. What I explained to you is chromatic dispersion, but that's not the only source of dispersion in optical fibers. So please be patient. I think in week 6 or 7, whenever we talk about optical fibers, these ideas come back again. Rajat has a question. For lattice mismatch, is the relation x by y is equal to 0.45 valid for every type of double heterostructure? No, no, no. This relation is valid only for that heterostructure that I showed you, indium gallium arsenide phosphide. It might be slightly different for different heterostructures. As I said, these are all empirical relations. So this will change with material, it will change with probably temperature also. You just pick from the handbook. All this information is available in the handbook. Any other questions? I'm going to be here for 3 more minutes until 6:15. Can they reach the, are they reach the destination at the same time? The different colors I thought you're asking. No, they won't reach the destination at the same time because they are propagating with different speeds. They're carrying the same information, but they're propagating with different speeds. So they don't reach the destination at the same time. And that's why the problem of dispersion is critical. Yes, Rajat. So it is valid only for that heterostructure as far as I know. So as you can see, some of these notes are actually ready. We're just waiting for some small thing to happen before it can be uploaded. We'll do that as quickly as possible. If you're finding any difficulty in the accessing the videos or material, just let me know. I also warn you that I strongly encourage, rather not want, encourage you to read some of the reference books and do not constrain your knowledge only to the lectures and the lecture notes. Please do read some reference books which I had suggested in the beginning of the course. Okay, so I'll log off and I'll meet you again next week. NPTEL team, can I log off? Yeah, thank you very much. Thank you. Have safe, good evening and stay safe, everyone.